Structural Modeling 2.0, Part 3, an application of basic structural modeling and interpretive structural modeling. This will be a review and an overview and a summary of this particular Structural Modeling 2.0 video series. You get the slides. This link will take you to my website. This link will take you to my Twitter feed and a Twitter account. So Structural Modeling 2.0 overview. So basically this video completes the Phase 2 video series. We've demonstrated a new web application. This web application has the following functions. It has integrated graphics, operations, and display. It's direct user information input. It has unique JavaScript math and matrix code. And it also has unique system structuring approach. We've integrated many of the functions of the structural modeling and structural system structuring activities into this one visual interface on this JavaScript web app. So fundamental concepts here are basically about truth, and there's three types of truth. There's formal truth, factual truth, and value truth. And this demonstrated approach with the visual JavaScript web app combines the formal and factual truth into one matrix grid. So we have empirical data, which is the factual truth, is entered into the grid. We go collect data, we collect information, we enter that information into the grid. And then inferred information, or formal truth, is calculated from the grid data. Value truth guides the matrix reconfiguration. This is something that where the user is doing this, but the value truth, we know that we have a final configuration of the matrix where we have all the ones in the lower matrix, the lower triangular portion of the matrix. So that's the value proposition that we want to have, or the most valuable configuration. So the value in this particular case is associated with the final known configuration that we want for the structure of the matrix. And then this particular matrix configuration is based on a strict subordination matrix pattern. We have 19 cities. We only allow one city at each level. Therefore, we have 19 levels. We know a lot of information and can infer a lot of information using the strict subordination matrix pattern. So the abstract relation type is based on real-world natural language relationships, and it's converted to a mathematical relation using relational properties. In this particular case, the relationship is north of. We're going to order these cities using the relationship is north of. And the properties of this relation, of course, are transitive, asymmetrical, and irreflexive. The strict subordination matrix forces one city at each level, as we've talked about, and the final system structure depends on both the relationship properties and the matrix type. So when we're looking at specific, or thinking about different types of abstract relation types, we're going to have to precisely communicate not only the relationship properties and the relationship name, but also the matrix type. Three types of truth. Of course, we have formal truth, factual truth, and value truth. And formal truth, of course, depends only on the form and logical connectives. Factual truth depends on the state of the real world. And value truth depends on a number of things, including ethics, culture, prediction, but it basically is associated with what people assign a high value to, and in this particular case we're assigning the value to the final structure of the matrix because that's what we want to do. We want to structure the system. And more information about the three types of truth. And of course, we can see here's the in the rows we have examples and attributes, and then each column is a different type of truth. Of course, formal truth is not known by experience, but factual truth is. Formal truth is not certain, is certain, but factual truth is not. So we're actually combining these aspects, and we're gathering factual information about a particular situation. Then we're using, and that's factual truth. And then we're taking that data and its formal rules associated with it, and we are computing, doing computations associated with that formal truth to infer more information. So our proof is necessary and sufficient. So we're incrementally building a system that combines both factual truth and formal truth. And of course, the purpose of this is to minimize the cost of gathering data. The abstract relation type has three general areas, three different parts. It has a marking space, an outcome space, and a value space. As we show here, we have multiple value spaces, but you can also have multiple marking spaces and multiple outcome spaces. Each one of these can be represented by a matrix or some other mathematical form. The abstract relation type basically has three main parts. It has a prose description, a graphic representation, and a mathematics and computer representation. The grid and what we're working on here and the mathematics that drive the grid are, of course, the displayed graphics and the mathematics piece. The artifacts that are on the website have the rest of the information about the abstract relation type. But these three types of information, we're putting those together so that we can have, in more of a formal sense, we have a formal prose and graphics and mathematics. One set of these representations can have a model exchange isomorphism, which allows you to represent the model in prose and the same model in graphics and the same model in mathematics, and basically translate in between any one of those and not lose any information. So our mapping context for complexity, we usually use system concepts in two different modes, design mode and the discovery mode. This particular case, we're in discovery mode. We know the objects, and we're discovering the relationships between each of the objects. Most people that use graphic types of systems are using those graphical representations in the design mode, where they know the relationships and are designing the objects to meet those relationships. But that's not in this case. In this case, we're actually discovering the system structure and using the system concepts in a discovery mode. So a system is a relationship mapped over a set of objects. We know the objects, which are the cities. We know the general relationship is north of, but we must discover the specific relationship between each city pair. And this discovery process is based on the empirical data that we collect and also the inferred data. We use these two concepts tightly integrated in the matrix, with the objective of actually minimizing the cost of structuring the system. Demonstrated features of this particular web application it is a JavaScript-based ordering process. It is integrated graphics, inference, and analysis tasks. We've demonstrated an integrated web application tool, which basically maximizes the use of inference, minimize the use of empirical data, and of course minimize the use of the cost of the structuring activity. There are very general process steps. Step 1, initialize the process. Step 2, you loop through these steps until you're done. Of course, the sub-steps in step 1 are identify the cities and create the initial matrix. And then the sub-steps in step 2 are obtain empirical data, order the structural information based on the value. We want everything in the lower triangular area. Infer additional information, and of course go back to step 2.1 until you're done. Cycle through that. So in our specific process marking for our types of truth, as we said, we are mixing formal truth and empirical truth on the same matrix. So formal truth designed from logic, and true and false are marked on the matrix. Empirical truth is derived from observation, and known and unknown is also marked on the matrix. And we combine these truth values, we mark them with different colors. So true, false, and unknown. True and false and unknown are the things that we're going to mark. True and false are actually known data, so we don't have to have a special marking for known data. Green equals true, red equals false, and yellow equals unknown. These are the color markings that we're using on the matrix. This is our beginning configuration for the web application. It has user interface buttons and then a display area. Once you click the Initialize City Grid, presents you with a main grid with the zeros with yellow backgrounds, which are unknown data, and then zeros on the diagonal with red background, which means false. And then the city name tags are here on the rows and columns. And in this particular case, City 2 is north of City 2. That's a red 0, meaning false. We're not going to allow a city to be north of itself. Again, we're going to go City 19 is north of City 19. Well, that again is a red 0, which means it's false. We're not going to allow a city to be north of itself. Then we went through and collected information and went through that process in detail. In the part 1 video, this was the graphic or the state of the grid at the end of part 1. We had a number of red zeros, we had a number of green ones, and we had a number of blue ones. So we go through and we collected empirical data. If it's true, we get a green one. If it's false, we get a red 0. And then the blue ones, these are inferred true data points that we get from inference and formal logic. And the more data you have as this builds, then also your percentage of inference capability also increases. And one of the things that we talked about and went through was actually how to maximize the inference potential in selecting things to look at. Now this is the end of the structuring process at the end of part 2. As you can see that we have many red zeros, which are false, the green ones, which mean true, and then of course all of the inferred blue ones data here in this particular process. So this is the ending part of once we've gone through and we've structured everything, and this then returns the proper ordering of the city name tags. As you can see in the the X and Y axis. So we demonstrated an inference operation. We used a unique JavaScript matrix functions. The inference function is readily available. You can use it at any time. That marks inferred information with a blue background and integrated into the program workflow. So structural integration modeling primarily has three basic components. Structural modeling components are basic structural modeling and interpretive structural modeling. These were developed by John Warfield. We've added structural integration modeling, which we use as the structured step that's actually in between basic structural modeling and interpretive structural modeling, and organizes names and gathers the data and the processes that are necessary to go from a basic structural model to an interpretive structural model. System integration frameworks enable structural modeling and methods and techniques. that's the end of this new series. I have another video series is planned. It'll focus probably on some of the other computing aspects and other computing tools associated with the basic structural modeling. Have fun.